So it's already time, so we start. I welcome everybody at the 11th lecture of our laboratory astrochemistry lecture course. The lecture will be given by Professor Martin McCoustra from Heriot-Watt University. So Martin, please, the floor is yours.
Thank you, Sergey. If anyone wants to send me an email message, so please take note of my email address. I'm quite happy to engage in discourse following this session for an extended period. So what I'm going to spend the time today talking about is essentially the laboratory astrophysics of solids and surfaces. One of the things you've all learned over the last few weeks is that there's a cycle of matter in the universe. Matter starts out in the low density dark regions, or very light regions, the diffuse interstellar medium. Gravity starts to bring that matter together into dense clouds, and it's in those dense clouds that we get star and planet formation. And ideally, we have the conditions for life and sustaining it. But stars get old and die, and eventually they will cycle back the matter that was part of their stellar system out back into the diffuse medium. There's lots of astronomical observations of this different environments in space. The first gas phase molecules were reported in the 1930s in comet tails. Of course, before that, we had an extensive atomic spectroscopy, which mapped out the composition of stars and added to our knowledge of the periodic table. The first reports of solid state materials, however, really waited until the development of infrared astronomy in the late 1970s and early 1980s. And that's when the more abundant solid state materials, water ice, carbon monoxide ice, and carbon dioxide ice were observed together. But really, if we're going to see something, if we see something there in a particular environment, then there's an obvious question to ask yourself. How did it get there? One way to explain that is by modeling, but actually the synthesis needs experimental verification. Now, for gas phase chemistry, there's a long-standing activity in looking at gas phase spectroscopy, and is increasingly supported with high quality computational chemistry nowadays. In terms of solid state material and interstellar ices, again, the work is more recent, and actually in many respects parallels the observational work. And the people here we can look to are Amendola and Greenberg, who pioneered matrix isolation techniques in solid state and surface laboratory astrophysics. We know there are well over 200 species in the gas and solid state. Lots of atoms and radicals and ions. There's lots of simple molecules. Many of them we know are in the solid state: water, CO, methane, ammonia. And there's lots of, and increasingly lots of, complex molecules. As a chemist, I will admit that very few of these molecules are what I would consider seriously as complex. They're just large molecules, or should I say relatively small molecules to a chemist. But they're complex from the point of view of essentially starting out with simple species, as in the line above, the hydrogen, the CO, the water, and the methane. Those are the first generation species. We then, through further processing, make larger molecules. That processing may be in the solid state, or it may be in the gas phase. It turns out that actually most of the complex molecules, or complex organic molecules, COMS, as is often talked about, are observed in dense regions in space. And these are known to be the sites of star and planet formation. And it's been realized that molecules are important for essentially maintaining the rate of star formation, for ensuring that we get small, long-lived stars like our own sun, and actually seeding the universe with a chemical potential for life. So molecules are really fundamentally important. And so it's important to understand how they are made. To help understand how they're made, we should look to the fact that there are different environments, and in those different environments, there are different conditions. In the diffuse interstellar medium, we're talking about pressures of 10 to the minus 14 millibar or even lower. Relatively modest temperatures, about 100 Kelvin, and exposed to a whole, essentially the whole electromagnetic spectrum. Really, in that environment, we only see protons and hydrogen atoms. We move into the dense region, and then we're getting into an environment that we can actually produce experimentally. 10 to the minus 9 millibar is at the upper limit of ultra-high vacuum. The most easily type, essentially the lowest vacuums that we can reasonably well reproduce in the laboratory. Temperatures in the dense medium can be as low as 10 Kelvin, perhaps even lower in certain dense environments that are quiescent. And because they're dense, we get attenuation of essentially high energy radiation. Really, in the core of a dense environment, we're only going to see infrared or radio frequency light, although there will be cosmic ray vacuum ultraviolet produced locally through ionization recombination processes. Going to stellar nebulae, we get higher pressure still and warmer temperatures. And we start to see that in these denser environments, we get more and more molecular material. More and more of essentially hydrogen and CO. Now, if we add in dust into these environments, that dust can be made from essentially silicate sources, or it can be carbonaceous in nature. That provides us additional surfaces on which we can get physics and chemistry occurring. That opens new opportunities for chemistry. I'm not going to talk about gas phase chemistry this afternoon. Wolf Geppert talked about that last week, but the graphic here nicely summarizes the wide range of gas phase chemistry that can occur. The predominant chemistry is essentially ion molecule chemistry. Reactions between charged molecular species or atoms and neutral molecular species and atoms. More recently, there have been experimental confirmations that we get some neutral reactions involving radicals, particularly exchange type reactions. And of course, there's a whole range of gas phase processes initiated by photons, by light, that ultimately may involve electrons and protons as well. That gas phase chemistry goes a long way to explain what we see in the gas phase. The observations that are made purely of the gas phase. The problem starts to be realized when we think about what we use chemistry for. We use chemistry as a clock to tell us how old an object actually is. And to do that, we build chemical reaction networks. These are essentially collections of the rate laws, the differential equations describing the chemical evolution of a particular environment. As part of those networks, people have provided over many years rate constants, activation energies, pre-exponential factors. We know what the photochemistry of many gas phase species looks like. And we can build that gas phase network and run it in our computers, simulating a particular environment like a dense gas cloud, just like we can simulate Earth's atmosphere. And we can try and predict the concentrations of more complex organic molecules and use the variation of those concentrations to assign an age to a particular object. Unfortunately, we find that gas phase only models have problems. They have problems in particular in predicting the concentrations of hydrogen, water, and other small hydride molecules. And the only way really to explain that discrepancy is to accept that dust is the key ingredient necessary to make these small molecules more rapidly than we would find in a clean gas phase experiment. Essentially, we're saying that surface chemistry is making these small hydrogen-rich molecules on the surface of the dust grains. So what we're thinking in terms of processes in solid state and surface astrochemistry is we've got our dust grain core, which might be silicate. It might be silicate with a little bit of carbonaceous material. It might just purely carbonaceous. Typically, the cores are relatively small, but by the time they've evolved in cold dense media, these particles can get up to about a micron across. If we start by thinking about what happens with hydrogen, hydrogen comes in, it lands on the grain surface, and then it dances around, diffusing over the surface until it finds a partner, and then the reaction enthalpy causes that partner to be kicked off, that product molecule, H2, to be kicked off. If we look at water and ammonia, well, the hydrogen atoms are mobile, the oxygen and nitrogen probably aren't, and the products are themselves not generally kicked off into the gas phase by enthalpy release. So we start to accumulate a layer of ice on the grain core. That accumulation, that accretion process may also mean that we accrete stable molecules from the gas phase by simple adsorption processes. The molecules there that are important are CO and potentially nitrogen. So we make an icy mantle on our grain core that grows with time. That icy mantle initially will start off containing essentially hydrogen-rich small molecules, CO, N2. It will be subject to heating. We'll talk about that in a few minutes, but more importantly, it will be subject to irradiation by cosmic ray ultraviolet and to cosmic ray impacts themselves. The cosmic rays and the ultraviolet light do a couple of things. We can cause desorption, photodesorption, or mechanical desorption, essentially kinematic desorption or sputtering, and electron-stimulated desorption. But that energy input also breaks chemical bonds. It will take a water molecule and convert it into hydrogen atoms and OH radicals. It'll take an ammonia molecule, make NH2 plus H. It might take methane and make CH3 plus H. Those radicals at low temperatures will generally be fixed in the icy mantle, but as we start to warm things up, they will become mobile in the mantle, and we can get radical recombination processes. The one thing I would add to that is that if we, in contrast, hydrogen is mobile under all the experimental conditions that we might have when irradiating such an ice. What the hydrogen atoms will tend to do is percolate out of the ice, often picking up a second hydrogen atom as a partner and leaving the ice as a hydrogen molecule. So UV photolysis and cosmic ray radiation has a slight tendency to dehydrogenate the ice and essentially start to produce unsaturated carbon centers. So dust is really crucial, especially in these cold, dense environments. Just to reiterate, it makes the small hydrogen-rich molecules that the gas phase chemistry has only gas phase chemistry has models have difficulties in reproducing. Some of those small molecules are going to be stuck to the grains. We can get condensation of other molecules from the gas phase on the grains. So the grain mantle, the icy mantle, acts as a reservoir of molecules, a reservoir of small molecules. And it's those small molecules that are important in radiatively cooling collapsing gas clouds. As the clouds start to warm from the cold dense into the early stages, the hot core, and beyond stages of stellar evolution. Equally, those icy grain mantles are little nanofactories driven by photons and cosmic rays to produce complex organic molecules containing multiple carbon atoms, oxygen atoms, ammonia atoms, nitrogen atoms. It may even be possible that in those environments we make prebiotic molecules, because we can do that in a laboratory by irradiating a simple mixture of water, methane, and ammonia. So if we're going to consider the surface science of the astrophysical solid and surface state, then we have to think like surface scientists. And you're always going, whenever you talk to a surface scientist about any particular complex system, they're always going to ask several key questions. The first one is, what's the surface made of? Well, we know that. We can say it's a silicate mineral. Iron, magnesium silicate is the common one, olivine that we use as a model. It might be carbon, but is that carbon graphitic? That's what the 217 nanometer absorption feature in the interstellar radiation curve is associated with. But it could be graphene. It could be small clusters of carbon, PHs. It could be hydrogenated amorphous carbon, which ultimately could be considered even nanodiamonds. And we know there are metal atoms out there. So the surface scientist wants to know what the surface is. And we can then look using particular techniques on our model surface to look at how that surface composition changes. For the most part, laboratory astrochemistry is focused on infrared. But X-ray photoelectron spectroscopy and Auger electron spectroscopy are much, much more common in surface science than infrared. And they're powerful techniques that tell us about the composition of surfaces. The next question is, what's the surface structure? Is it crystalline? Is it amorphous? Do we have some sort of extended nanostructure? There we have to use a combination of microscopy, scanning or transmission electron microscopy, or scanning probe techniques, or computational chemistry to tell us what the structure of the surface actually is. One thing for sure, that surface is not going to be single crystalline. The next question is, what species are we interacting with the surface? Well, our gas phase composition gives us a guide to the dominant species that we should be looking at. And there we would be using mass spectrometry to monitor the gas phase with the sensitivity that we need when doing these experiments. And finally, we get to the biggest question. What physical chemical processes are important on the surface? Certainly, things adsorb at the surface, things desorb at the surface, things diffuse over the surface, and we'll get reaction. Those are the processes that we need to investigate. What I'd like to quickly go through is, how do molecules adsorb on surfaces and how we classify them? And the idea goes back to work by Leonard Jones in the 1930s. Here we have two axes, a vertical axis, which is potential energy, and a horizontal axis, which is distance from the surface. Leonard Jones postulated that there were two types of interaction. At large distances from the surface, he said there was essentially van der Waals interactions. non-covalent forces holding the molecule on the adsorbate on the surface. This is physisorption. The key thing is the distance from the surface is large and the depth of the well is very small. Lennard-Jones also indicated that was likely to be a closer in type of adsorption, which usually involved breaking chemical bonds. And this he labeled chemisorption. Essentially involves electron transfer between the adsorbate and the surface, the formation of a new chemical bond at the surface. And so the well depth is much deeper than in the case of physisorption. Now we can put a few numbers on that diagram. The well depths, that's the distance below the zero in potential, are called the enthalpies of adsorption. Enthalpy is released when something adsorbs on a surface. A small amount of enthalpy when it's a physisorption, a larger amount when it's a chemisorption. To get anything out of those wells, we'll require to put energy in, an activation energy. In the case of physisorption, the activation energy for desorption is numerically the same magnitude as the enthalpy of adsorption, except that we're putting that energy in to get the adsorbate off the surface. In chemisorption, the activation for energy for desorption is generally larger than the magnitude of the enthalpy for adsorption. And it's larger, particularly in the case when there is an activation energy for adsorption, when we properly account for the energy required to break any chemical bonds prior to adsorption. So to summarize, we can classify adsorption of atoms or molecules onto surfaces in two ways. We have physical adsorption or physisorption, chemical adsorption, and chemisorption. Physisorption, long range, involves weak van der Waals interactions, perhaps even some extent hydrogen bonding interactions, essentially non-covalent interactions. The binding energies are typically less than 50 kilojoules per mole. And the adsorbate on the surface is largely unperturbed by its interaction with the surface. In chemisorption, it's a short-range process involving electron exchange between the adsorbate and the substrate, and us getting some form of covalent bonding. Binding energies are much higher. And potentially the adsorbate will be very significantly perturbed by interaction with the substrate. Now, at this point, I'm going to make a very important point from essentially a surface science perspective. When we change an environment in space, all we are changing are the boundary conditions that apply in that system. Temperature, composition, radiation field. We will fundamentally not be changing the basic physical chemical processes occurring at the surface. Adsorption is adsorption wherever it occurs in space. Desorption is desorption wherever that occurs in space. So the processes that we see as surface scientists don't change, just the environment in which they are occurring. So how do we go about looking at chemistry and physics on grain surfaces? Well, in my particular group, we have a couple of machines that are set up. I'll show you a picture in a moment. But basically, we start with with a metal substrate, which is optically flat and polished. And it's cooled either by liquid nitrogen or a closed cycle helium compressor. So we cool it to below 100 Kelvin. We can grow on that polished metal surface an overlayer reflecting the nature of the grain material. We tend to grow amorphous silica. Other people might look at carbonaceous materials. We choose to grow it as a thin layer on top of a reflective surface because that allows us to use reflection absorption infrared spectroscopy and to benefit from the enhancement in the surface infrared signal due to reflection at grazing angles. Reflection absorption infrared spectroscopy is typically some 40 to 60 times more sensitive than transmission infrared. That basically means I can work with monolayers and submonolayer quantities of strongly infrared absorbing species. Above the surface, we will tend to put a mass spectrometer. And then we have ways of introducing atoms, radicals, and molecules, light, electrons, and ions, so that we can probe what's happening under or on the surface using the infrared, and we can see what's coming back from the surface using the mass spectrometer. The reality, of course, is much, much more complex than the cartoon. This is one of my two machines in Edinburgh. You can see the optics boxes here for the infrared. The mass spectrometer you can't see because it's sitting down here. This system also contains two atom beamlines that we can use to irradiate the surface with atoms that are generated using plasmas. And more recently, we've added capabilities for doing Auger electron spectroscopy to the system and dosing clusters of metal atoms. It took us a number of years to build this machine. The initial version of it was built at the end of the 1990s when I was still at Nottingham, and then we extended the machine significantly up here at Heriot-Watt University. The rest of the stuff around there is just pumping. So what does our surface look like? Well, this is our surface. It's amorphous silica, which is generated using electron beam evaporation from solid silica onto a room temperature, optically polished copper substrate. You can see the size of you can see the morphology in this AFM image. It's not a flat surface. We've got almost as much vertical surface, that is vertical with respect to the substrate, as we have horizontal surface. And that has an advantage. It gets us around one of the problems of doing reflection absorption infrared spectroscopy directly on metal surfaces. And that's the metal surface selection rule, which limits the selection rules on metal surfaces. That surface is polar. We'll come back to why that's important in a moment. So let's look at these processes I talked about, absorption, desorption, etc. We need to consider what happens when we take a few simple molecules like CO, water, or ammonia. The key thing is the rate of adsorption. That's given by this relationship here. The rate of adsorption depends on the sticking coefficient times the partial pressure of the adsorbate in the gas phase, where Mi here is the mass of the adsorbate, an individual adsorbate molecule, and T is the temperature of the gas phase. So we can work out the rate of adsorption, provided we know the sticking coefficient. Well, generally we don't, unfortunately. So we often make an assumption that at sufficiently low temperatures, the sticking coefficient is 1. Everything sticks. And that's probably true below 10 Kelvin. Maybe 20 Kelvin. The sticking coefficient itself is, as it says, it's a number that varies from 0 to 1. And it depends how much material there is already on the surface. It depends on theta, the coverage. Up to a coverage of a monolayer. Generally then, when we've got a monolayer of material, the sticking coefficient will stay constant. It also depends on, of course, the surface temperature. There are 2 limits of behavior that we often talk about. The first is the simple situation where molecules are coming down, randomly sticking on the surface, and there are no interactions between them. That's what we call linear adsorption. And in linear adsorption, the sticking coefficient varies as 1 minus theta. We have the initial sticking coefficient times 1 minus theta. Now, I should say in passing that theta is essentially the number density on the surface of the adsorbate divided by the number density in a monolayer of adsorbate. Where we have interactions, this relationship gets a little bit more complicated, and we have what's called Kislyak adsorption. So a key experiment would be to measure S. The problem is most experiments designed to measure S don't do so. They measure what's called the uptake coefficient. And that's because when you look in detail at what's happening on a surface, when you have an input flux of molecules from the gas phase, some will be adsorbed, some will be reflected. And some of the adsorbed material will, after a certain amount of time, desorb. That latter process intimately depends on the surface temperature. It's very easy to show that the uptake coefficient as a function of surface temperature can be written in terms of the sticking coefficient as a function of surface temperature and the rate of desorption, the rate constant for desorption as a function of surface temperature. Only when alpha is negligible, only when this term disappears, I should say, when there's no desorption, does alpha give us a value of S. The most common experiment applied to measuring S is the King and Wells method. And this is a molecular beam method. So we have a molecular beam sitting in front of our, it says crystal, in terms of our sample. The beam is initially blocked from the sample and is scattering from this flag. We detect the scattered gas in the mass spectrometer, the QMS. We take the flag out, and the surface suddenly sees the beam. The surface behaves as a pump, and there are pressure changes that we can follow with time. So in a King and Wells experiment, we get a partial pressure time trace that would start out down here before we introduce the beam. We turn the beam on and the pressure rises because it's scattering from the flag that it doesn't want to stick to. When we take the flag out of the beam, the pressure drops because the surface is now seeing the beam. There's a reduction in the background pressure. We then start to fill the surface and the pressure rises back to that upper limit. There are two pressure changes on there, and we could define the sticking coefficient as a function of time in terms of the ratio of the two pressure changes. The area under this, or in this curve, this area here, tells us how much material has been absorbed in total. So if the absorption stops at a monolayer and we know what the surface coverage of the monolayer is, then we can work out S of theta. An alternative technique was worked out or developed in the 1990s by Rob Jones at the University of Nottingham, and that's a technique that we tend to use. And this is essentially a line of sight sticking probability method. Here we have randomly impinging background gas hitting the crystal rather than the molecular beam. We define where the gas is coming from that's detected by the mass spectrometer using a line of sight cold shield. And we swap the sample surface that we're interested in with an inert reflector that reflects back all the molecules. So it's a little bit like the King and Wells experiment turned on its head. In this case, when we turn the gas on and it's looking at the crystals, initially a quick rise, and then there's a very slow rise that represents the time when we're filling the crystal. It rises to maximum value when the crystal is full, when there's no more absorption. And of course, turning the gas off, we get a pump down curve, which coincidentally we can use to measure the pumping speed of the vacuum system. We swap the crystal out for the inert reflector, and we get a much larger jump in pressure, rising to a steady state. Again, two pressure changes, and we can get S once more. And if we know what the area within this part of the curve is, then we can work out S of theta. The King and Wells and the line of sight methods really only give us sticking coefficients down to about 0.05. If you want to get smaller sticking coefficients, then we actually have to use what's called calibrated uptake measurements. We have to measure the surface concentration of an adsorbate as a function of the dosed amount of the adsorbate. To do so, we need a calibrated surface-sensitive spectroscopy. Could be XPS, it could be Auger, it could be infrared spectroscopy, it could be TPD. As I say, we measure the surface concentration versus exposure, which is essentially the total number of molecules incident on the surface. The sticking coefficient is basically the derivative of this curve at any instant. So S of t is essentially derivative of this curve at any instant. Now, when you do adsorption, you can actually sometimes get surprised. Chemical intuition would tell us that if we've got a dipolar molecule, it would tend to absorb with the dipoles counter-aligned to minimize the energy of the system in the solid state. We wouldn't expect it to deposit like in the figure B, with the dipoles co-aligned. That's a high energy state. There's incredible amounts of repulsion between the dipoles. If we look at carbon monoxide as an example of a dipolar molecule, experimentally, we find B. So our intuition is wrong. How do we know we find B? Well, we actually see a splitting in the infrared feature of solid CO. Instead of seeing a nice single band, we see a pair of bands. And the splitting between those bands, which are the longitudinal optical and the transverse optical modes, changes with temperature. The splitting gets smaller at higher temperature. Now, what's happened here is that in depositing the CO in that dipole-orientated form, we generate a spontaneous electric field in the solid. And that electric field causes stark splitting in the vibration. That's why we see the two modes. The field is temperature sensitive, and as it gets smaller at higher temperatures, we see less splitting. Actually, not just carbon monoxide, but amorphous solid water, ammonia, methanol, all those simple polar molecules that are so important in the initial phases of ice grain growth are spontoelectric. They express electric fields in the solid state up to 10 to the 8 volts per meter. We see it by infrared spectroscopy and the vibrational Stark effect. Other people observe it by directly measuring surface potentials. We tend to find that these potentials increase the thicker we make the films and decrease with increasing deposition temperature. So why is this microscopic phenomenon important? Because it helps to fill an important gap in our understanding of the evolution of pre-stellar cores. Icy dust grains with CO ice mantles or water ice mantles will reduce the degree of ionization of pre-stellar cores by a factor of between 5 and 6. That will, in essence, switch off, that reducing the degree of ionization, switches off the magnetic support of these cores, and star formation can start. The observation of this behavior in low temperature solid CO and water and methanol, and the fact that we can calculate a 5 or 6-fold reduction in ionization, essentially explains a discrepancy between the observed rate of star formation and rates based on models that don't include the effect of the spontoelectric nature of small molecular ices. So I find it quite cute that a nanoscale chemical process has a massive effect on managing and accelerating the rate of star formation. So I've been talking away now for about 50 minutes. I'm going to take a short break now so that people can go and get a quick drink or visit the toilet. And then we'll start back again at, well, 3:05 according to me in the UK, but 4:05 in Central European time. So I'm taking a pause for now. Please come back in 10 minutes. Okay, that's, according to my watch, 5 past the hour. So we've had about 10 minutes. Hopefully everyone is back. If that's the case, then we'll begin with the rest of the presentation this afternoon. So we've looked very briefly at adsorption. That's basically taking a molecule that's been formed in the gas phase and depositing it on the cold surface. What about actually making molecules on surfaces? Or more importantly, transforming simple molecules into more complex species using light or cosmic rays. Well, there are a couple of things we have to consider. First of all, the environment. Are we in a cold, dense environment or a warm, diffuse environment? Then we've got to ask ourselves, what's our substrate? Silicaceous, carbonaceous, or ice? And what do we need to measure? In an ideal world, we'll measure reaction efficiencies and their temperature dependence. That's what we need to put into models. We also might want to understand the mechanism and dynamics of the process. Understanding where the enthalpy release, if there is any associated with the chemistry, goes. So let's start by looking at hydrogen formation as a nice example of what has been achieved and can be achieved in terms of studying molecule formation. So on the right-hand side here, we have a graphic taken from a review article by Gianfranco Vidali, describing the apparatus that his group used to explore the formation of hydrogen. Now, the important thing here is that at temperatures below 20 Kelvin, physisorption excuse me, dominates adsorption of hydrogen or deuterium atoms. Most of the experiments looking at this chemistry essentially followed a very simple procedure. They would dose on hydrogen atoms and or deuterium atoms at very low temperature, where the diffusion rate is very low. And then, given that the chemistry is Langmuir-Hinshelwood in nature, they'd warm up the surface very quickly to a temperature where they followed the reactivity. Diffusion would occur, hydrogen molecule formation would occur. There'd be some desorption, but not so much that they couldn't do a TPD afterwards to measure the total amount of hydrogen produced by Langmuir-Hinshelwood chemistry. And it turns out that this kind of Langmuir-Hinshelwood chemistry involving hydrogen and deuterium probably accounts for most hydrogen formation in cold, dense environments. It's very efficient. Just to show you the kind of data they're getting, on the left here, we have some of their TPD. So they're depositing at 5 or 6 Kelvin, H and D in a known ratio, and then they're heating up the surface slowly enough so that the diffusion kick starts, the H and D starts to react, and they can see HD formation, H2 formation, and D2 formation. They then essentially build a kinetic model, which they then extract from that model the recombination efficiency as a function of the surface temperature. And that's the information that you need to go into one of your astrochemical models. We can go a little bit further with that experiment, and this is the experiment by, or an illustration of an experiment that Steve Price at UCL and Francois Deleu in Paris actually put together. Here they recognize that the formation of the hydrogen-hydrogen bond releases something like 4.2 electron volts of energy. That's more than enough energy to start kicking the hydrogen molecule off the surface. It's more than enough energy to excite vibrations within the hydrogen molecule. So in this version of the experiment, they're using laser-based spectroscopic techniques to investigate the energy of the hydrogen molecules released into the gas phase. And they find that there's a lot of vibrational and rotational excitation. Consistent, actually, with computational chemical simulations of recombination on the surfaces that are relevant here. Graphite in the case of the Price experiment, and graphite and olivine in the case of the other experiment. Now, the important consequence of that chemistry is, if this is an efficient process in producing H2, that H2 is going into the gas phase now vibrationally and rotationally hot. It's going to change the energy balance of the cold dense regions. And it's potentially going to allow gas phase reactions that might not normally occur if the hydrogen is just cold. And really, this set of experiments going back to the to 2010-ish has prompted a search for hot hydrogen emission in these kind of cold dense environments. We can look in even more detail when we move to warm, diffuse environments. On the right-hand side, we have a set of images, STM images, of hydrogen atoms on graphite. And these are chemisorbed hydrogen atoms, because in the warm, diffuse environment, there's sufficient energy for the hydrogen atom to get over an activation barrier and chemisorb on the graphite surface. We also see similar behavior on graphene and pH surfaces. And this imaging work tells us what the favored geometry is for the hydrogen on the surface before it desorbs. Basically, the STM allows us to see hydrogen atoms and hydrogen dimers at very low temperature before they leave the surface. And this can be supported by high-level computational chemistry. Hydrogen is obviously important, but equally important and changing with time is the formation of more complex materials: water, methane, ammonia. We know that the early chemistry must be dominated by hydride formation and hydrogen atom addition reactions. And since around about 2005 or so, there's been an extensive amount of work looking at hydrogenation of carbon monoxide up through to methanol, but also oxygen atoms, nitrogen atoms, and carbon atoms. And extensive networks with measurements of reaction efficiency are now well established. And these experiments have relied entirely on using infrared spectra, looking at the appearance of bands associated with the simple molecules. There's a problem, however, that when we start to make more complex molecules, when we've got to environments, cold, dense environments where H2 dominates the gas phase, then we're really looking at radiation-induced chemistry in simple ices. And we're going from 1 carbon species to 2 carbon species to 3 carbon species to more carbon species. And infrared spectroscopy becomes less and less useful. We need to find other tools that allow us to observe the products. And one of those tools is mass spectrometry. Now, in this particular experiment from Ralph Kaiser, they used a tunable vacuum ultraviolet laser source to photoionize desorbing species from an irradiated ice. The photoionization the efficiency of photoionization depends on the structure of the molecule. So by changing the wavelength of the ionization laser, you can get additional information that helps you identify the species that have been produced in the ice. You could also do that by having a much more sophisticated mass spectrometer, one in which you can measure directly the parent mass with about 1 part per million sensitivity. That kind of high resolution mass spectrometry really then allows you access to identifying chemical species. It's the same tool that we're using often in analytical chemistry to identify substances of abuse. Now, one of the things that most, if not all, of the chemistry that's been investigated in ices to date have failed to look at is the presence of catalytic elements in the grains, the grain surfaces. Iron and nickel are incredibly important catalysts industrially. They're both involved in Fischer-Tropsch and Haber-Bosch type processes. And this type of catalysis, relying on the presence of either single atoms of metals deposited from the gas phase on grains, or nanoclusters of metals that have been produced by space weathering of the grains, is likely to be important in environments where the grain has no icy mantle. So in diffuse environments, in warm environments, in environments where H2 and CO are the dominant gas phase species. H2 and CO, of course, being the input into Fischer-Tropsch catalysis. So we've made molecules. Then we have to think about how we actually return the molecules to the gas phase. Because the gas phase is still the best place to detect them. We've got very, very nice spectra coming out of GWST, but trying to identify complex organic molecules in a solid spectrum, an infrared spectrum of a solid, is very, very difficult. It's easier when we've got rotationally resolved gas phase spectra. So how can we return molecules to the gas phase? Well, we can collide them off the surface, sputter them off the surface. We can heat the surface up, or we can have non-thermal processes. Let's just look at those three. I should add that desorption is closely linked to diffusion as well. Collisions can promote diffusion. At the kind of low temperatures we find in space, thermal energies of a few tens to hundreds of millivolts, or tens of millivolts, are too small to break even physisorption interactions. But they can induce diffusion. Interestingly, it hasn't been studied, so there's an open gap there. I will add that studying diffusion on surfaces is very, very difficult. But collisions can also promote desorption. If we've got enough energy, for example, in shocked regions, then we can induce desorption by collisions. Cosmic rays can do this as well. And this is purely a kinematic effect. It's conservation of momentum. And even when we go to the stage of having a protoplanetary disk, grain-grain collisions could induce desorption. And there are a number of groups around the world I know looking at or trying to look at single particle surface science. Heating, well, activates desorption, diffusion. And we need to understand diffusion if we're going to really understand the structure of ices on grain surfaces. If we're going to understand the idea of whether things wet or de-wet substrates. Water, as I'm sure you're all aware, is a polar molecule. Silica, I've already said, is polar. Polar molecules should wet polar surfaces. Very simple piece of physical chemistry. Here are the TPD data for water from our amorphous silica surface. And what we find is that even at half or 0.055% of a monolayer of water on our surface, we get desorption that's consistent with multi-layers of water. We get what's essentially called zero-order desorption. And that tells us that the water doesn't wet the silica. It's diffusing around on the silica and forming clusters and clumps of water. It does the same actually on graphite. And we can use infrared spectroscopy to tell us how fast that process occurs. And it occurs even at 18 Kelvin. The measurement is very simple. We measure the increase in, we put a fixed amount of water on the surface and measure the increase in intensity of the hydrogen bonded OH stretch as a function of time. Now, the student who did this experiment didn't take an infinite amount of time. He just actually after about 8 hours, heated the surface up a little bit and then cooled it back. That way he encouraged everything to agglomerate. We can get, from this variation in intensity with time, we can get the rate of agglomeration. And if we do this as a function of different surface temperatures, we can get the activation energy for diffusion of water on our amorphous silica surface and on graphite. On silica, we have the data here below 25 Kelvin. You have a roughly 2 kilojoule per mole barrier. Above 25 Kelvin, there's absolutely no barrier to diffusion of water on silica or on graphite. Now, benzene, on the other hand, is a non-polar molecule. It shouldn't wet silica. But again, if we look at the TPD, here's the low coverage data. Here's the high coverage data. These are all submonolayer quantities in the figure A. We've got evidence of a clear monolayer on the amorphous silica surface before we then grow a multilayer and go into zero order desorption. So our chemical intuition isn't working. If we swap benzene for cyclohexane, then we get zero order behavior again. And the cyclohexane doesn't wet the silica surface. So why should we get this failure in chemical intuition? Well, this is where it's useful to actually sometimes do a little bit of calculation. And we looked at a very simple cluster model for the silica surface and calculated the interaction energy between the cluster and benzene and the cluster and cyclohexane after we corrected for basis set superposition error. In the case of cyclohexane, we've got a very small binding energy, very weak interaction, physisorption. Here, on the other hand, we've got, with the benzene on the left, we've got a much stronger interaction. In fact, it looks like the benzene is transferring some electron density to a silicon atom. That isn't surprising. Silicon can accept that electron density, and we get a relatively strong interaction. So we have essentially this more like a strong physisorb or a weak chemisorb state for benzene on the silica surface. Of course, thermal processing promotes desorption. And the best example I can give you is our work on CO on water ice. And it reflects here the number of processes that's happening. CO is porous. A water solid at low temperature is porous. You put CO on top of it, it's like putting ice cream on a sponge. The ice cream will melt as it starts to warm up, but water is a little bit strange, and that porosity starts to collapse, trapping CO. And that trapped CO is only returned when the water ice crystallizes and ultimately desorbs. When we do the TPD, we don't see one peak for CO leaving water, we see 4 peaks. We see the multilayer of CO. Then we see monolayer CO bonded to the water surface. Then we've got a big gap when the CO that's been trapped is held in the ice matrix. The ice matrix crystallizes, we get this molecular volcano. And there's some residual CO that's leaves when the ice itself completely goes. Now we constructed a model to explain this, in eventually fitting that model to the experiment. I think we only had 2 or 3 parameters we had to vary. The rest coming from other experiments that had been done around the time. The advantage now having that model is we've got something that we can use to tell us what happens when we swap from laboratory heating rates to interstellar heating rates, from millikelvins to picokelvins. If we assume a heating rate of 1 Kelvin per millennium, sort of forming a hot core, before we did our experiment, this is the view of CO evaporation from the ice film. It all left at around about 1920 Kelvin. After we did our experiment, now you see there are multiple desorptions. And this has an impact on the chemistry in the gas phase. It changes the chemistry in the gas phase. Now, the obvious question is what happens when you look at other species? Well, not long after that work on CO, we did a very quick survey of a whole range of different types of material. The first type of material were those materials that hydrogen bond to water and will only come off when the water ice itself desorbs. Then we've got materials that, if they're made in the ice, are going to be trapped in the ice, but if they're deposited on the ice, are not going to have the ability to diffuse and are not going to get into pores. So don't trap well. Things like H2S and acetonitrile. There you tend to just see the sort of molecular desorption if it's sitting on top, and if it's put into the ice, you only see the trapping, the crystallization and other, the molecular desorption and the volcano feature. Then we've got things that can diffuse and get into pores. There you see the 4 peaks. And then there are a whole lot of other stuff that our astronomy colleagues said, could you look at? And we said, no, we don't want to look at those because they'll ruin our ultra-high vacuum system. But most of the things were actually metals and sulfur and phosphorus, things that are essentially refractory and really are going to, the water's going to leave way before any of these materials desorb. We know that that's had a significant effect on modeling. So what about non-thermal processes? Can we excite, for example, a vibration using light? There's an abundance of infrared wavelengths in the interstellar radiation field. It also penetrates into dense environments better than shorter wavelengths. And mid-infrared photons have energies that are larger than typical weak physisorption interactions. So potentially these should be able to cause desorption. Now, when I first wrote this slide last year, I said, watch this space. And what I would suggest, I would direct you to do is have a look at the recent Faraday discussion in Baltimore last June, where there's a report on infrared photodesorption. It turns out to be as efficient as vacuum ultraviolet photodesorption. That brings us to electronic excitation. Generally, when astronomers think about electronic excitation, they think about vacuum ultraviolet light, Lyman alpha. But we should not forget that the maximum flux in the interstellar radiation field is in the visible. So we need to consider visible and long wavelength ultraviolet. We also have to consider cosmic rays and their secondary electrons. And in fact, evidence is increasing that the secondary electrons from cosmic ray interactions are the most important progenitor for chemistry in ices. What do we need to measure? We need to measure reaction efficiencies, their temperature dependence, etc., etc., etc. We should also measure try and measure dynamics, because it may have importance in the environmental energy balance. So the kind of experiment is shown here in cartoon. We have our surface. We can shine on electrons or a laser beam. We have a mass spectrometer, and we can do two experiments. We can do kinetic experiments where we measure the rate at which molecules leave the surface as a function of time during irradiation, or we can do time of flight experiments to measure how fast the molecules are leaving the surface. We looked at electron and photon stimulated desorption of benzene from water ice. When we look at the photons, if we take 250 nanometer photons, we see clear evidence for photon stimulated desorption. Benzene absorbs around about 250 nanometers. So the benzene is acting as the antenna, pulling the radiation in. What we find, not just the benzene comes off, but we get water desorption. The benzene pulls the energy in, transfers it to the water ice matrix, and some of the water ice matrix desorbs. Remember, at 250 nanometers, you've got about 5 eV of energy. And its cross-section for that process is not dissimilar to the cross-section for photon absorption. It's about 10 to the minus 19 square centimeters. It's also quite efficient. The quantum yield for water in this experiment was about 0.25. Looking at the benzene and looking at the water as they come off the surface, we see that basically when we look at the dynamics, we can separate out different processes. There's a process that depends on the substrate being excited. The substrate was sapphire, and I'll be honest, all of us involved in those experiments forgot that sapphire absorbed 250 nanometer light. So essentially we had a laser-induced thermal desorption. We have the adsorbate-mediated effect, which changes strongly with wavelength, reflecting the absorption spectrum of benzene. And the presence of a capping layer kills off the water desorption. We know that the water is coming off not just as isolated molecules, but as clusters, because here we see time of flight data that we can't explain using isolated water molecules. So we're getting water cluster desorption. And we need the benzene to kick the water off. If we look at electron-based processes, we actually see a very efficient desorption of benzene. We don't see so much desorption of water. But the benzene desorption in this instance is mediated by the water ice. So the energy this time isn't going directly into the benzene as it was with UV photons, it was going into the water ice. We're electronically exciting the water. And although in the gas phase water dissociates, in the solid state, it lives long enough for energy transfer to occur along a hydrogen bond chain network until that excitation gets up to the surface of the water, and then relaxation occurs, kicking off the benzene. Now, the important thing here is that the cross-section for the desorption is much higher with electrons than with photons. This is a much more efficient process. And interestingly, we checked. We saw no evidence for any chemical transformations in the system, only desorption. We then explored what happens if you change from water to methanol and to ether. Well, we've got to here think about the different structures. Methanol has hydrogen bonding, but it only has linear hydrogen bonded chains. Solid methanol does not have dangling OH groups at which benzene can be absorbed. And so if we look at that red curve, there's literally no desorption of benzene. The tiny little bit at the beginning might be due to a little bit of heating by the electron beam. And there's, again, when we go to ether, there's no evidence for that energy, that fast energy transfer process that involves hydrogen bonding. Because there's no hydrogen bonding in ether. The C6H6 interacts with the benzene through van der Waals interactions. And really what this set of experiments was telling us is if we're looking at this kind of energy transfer in water ice and other matrices, we've got to think about the hydrogen bonding as a way of network, as a way of transferring energy from where it might be absorbed in the near surface regions back to the surface to desorb species. What we did see in these systems, particularly the methanol and ether, is a lot more hydrogen production. There's competitive processes to the energy transfer involving relaxation of the excitons in methanol and ether that produces or dissociates CH bonds. Now, what we then did is we took these results and we started to build a nice, simple model. We looked at thermal chemistry, we looked at photodesorption involving the interstellar radiation field, we looked at the cosmic ray processes, and we looked at the electron-induced processes. And the key thing is these processes all involve some rate constant that effectively involves summing over a spectral distribution. If we look at the steady state, the important thing is that you can see the contributions here at the steady state. This is AV0 right at the edge of a dense environment. The edge of a dense environment, the external interstellar radiation field dominates, but you can see immediately that the electron stimulated processes are going to be much more important than those promoted by the internal ultraviolet field in the dense environment. If we go to AV6, it becomes even more clear that the dominant process for desorption, non-thermal desorption, is that induced by secondary electrons. If we think that about thermal desorption, well, basically at AV0, thermal desorption is irrelevant. because the photon-driven processes dominate. When we go to AV6, there's a region where the time scale where the photon-driven processes dominate, switching over to where the thermal processes dominate. We can add reabsorption into that model, and we can look at essentially a quiescent environment and see, do the numbers match with what we know about quiescent environments? And yes, they do. So we come to the conclusions, and hopefully we've got a few minutes left for questions. Surface science really does have a key role to play in understanding the physics and chemistry of astrophysical environments. We can model in our laboratories the likely processes that happen, whether we do those models experimentally or in our computers. Really, those processes are therefore, in my opinion, universal. And that includes the processes taking us to the edge, taking chemical complexity to the edge of life. Astronomers are finding exoplanets more and more regularly. Okay, a lot of them are massive Jupiter-like things, but increasingly we're seeing numbers of small Earth-like planets. There are new missions planned to look exclusively for small Earth-like planets. I would argue that given the universality of chemistry that we model, whether it's gas phase chemistry or solid state and surface chemistry, there's every chance of the chemistry that occurred here 5 billion years ago occurring in other environments in our galaxy and potentially in other galaxies. And really, surface science is the only tool that can help us to address the questions arising about the origins of the complexity necessary for life. Thanks for listening.
Thank you, Martin, very much for this very interesting and informative lecture. So it is now open for questions. So please, everybody ask question in the chat. So meanwhile, I think I can start with one question from me. For example, it's commonly considered that very large organic molecules are formed only due to the surface reaction. And these large organic molecules are almost impossible to detect in the observation in ices.
Yes.
So would it then mean the laboratory astrophysics is the only way to define the presence of these molecules in the dust grains? What is your opinion?
Yeah, it's an interesting question, Sergey. I think there are experiments that seek to address this. I know Stephanie Millam is coupling thermal desorption with Fourier transform microwave spectroscopy. And so there the goal is basically to do a, start with a basic ice, cook it with light or electrons, and then after certain times desorb it and measure the spectra of the complex molecules directly. Once we can do that, and we can also identify them by secondary means like high resolution mass spectrometry, it makes it much easier to then go out and look for stuff using ALMA. The limiting factor in terms of linking the solid state to the gas phase is simply we do not have all the necessary standard spectra of the potential molecules that might exist. It takes time to measure that. It's probably the next 20 years worth of experiments in this area.
Okay.
I noticed that we have a question there. What is the necessity for doing BSSE? The reason that I had to do basis set superposition error corrections was I was using Hartree Fock codes. I was not working with DFT. It's always a necessity when you're doing Hartree Fock to make that kind of basis set superposition error correction.
Oh, so the next question is, how is dust, carbon or silicon grains are formed in the ISM?
Okay, if we think about the first generation of stars, the first generation of stars were large. They probably went off on the asymptotic giant branch in the Hertzsprung-Russell diagram, and they went to AGB supergiants. Certain AGB supergiants have more carbon in them than oxygen, and these tend to produce carbonaceous dusts in their stellar outflows. So PHs, nanodiamonds, things like that. We also have AGB red giants who are oxygen rich. There the carbon tends to be converted into CO, but we also in those environments find metal oxides like silica, iron oxide, titanium oxide. These become inorganic oxide dusts in stellar outflows. They get into the diffuse medium. There will be some degradation due to environmental effects, space weathering. You'll start to get recombination, but eventually you end up, well, eventually they'll be recycled into the next generation of stars, and so it all starts over again. So really it goes back to, you know, the AGB red giants making either carbonaceous materials or oxides and flooding them out in their stellar outflows into the diffuse interstellar medium. I hope that answers your question.
Yeah, thank you. So the next question. New molecules are being discovered in clouds, but there are no matching spectra from laboratory astrophysics. How can we go about identifying them when we don't know exactly what we are looking at?
That is the crux of the matter at the moment with observational astronomy. The throughput of measuring spectra in the laboratory is limited. There are only so few groups who do it. And to be blunt, it's not a priority. These groups often get paid by pharmaceutical companies to help them identify the structure of pharmaceutical molecules. And they'd rather spend their time doing stuff they get paid to do rather than stuff that no one is willing to pay them to do. And that's part of the problem. The astronomy community is unwilling to pay for the service for gas phase spectroscopists to do the necessary measurements. It will come, but it's going to come very, very slowly. And it will come in parallel with improvements in computational chemistry, such that in a couple of decades' time, I suspect you won't ask that question because you'll be sitting down at your computer calculating what the spectrum will look like for your unknown molecule.
Is it already possible?
It is, but it's not quite good enough to get. It is for very small molecules, water and such like. But when you get to larger organics, there are too many low frequency modes that have to be have to be handled properly. And those, unfortunately, are the modes that turn up in the ALMA region.
Okay, thank you. So the next question is, if I recall correctly, you said that when it comes to the CC species formation, infrared technique becomes less useful.
Yeah.
Why is it the case? Is it in general or only applicable to large organic hydrocarbon molecules?
It's generally the case that as you make molecules bigger, their infrared spectra become more complex. And given that most, admittedly the resolution in JWST is good, and we can get better resolution in the laboratory, there are limitations in the solid state. Typically in the solid state, because of rapid relaxation of vibrationally excited states, line widths are often one or two wave numbers wide. If you were to look at a whole range of, for example, if you take the alkane series and looked at all the infrared spectra at a resolution comparable to JWST, for example, 3 or 4 wave number, all the spectra look identical. If you took the homologous alcohol series, methanol, ethanol, propanol, again, all the spectra look pretty much identical when you get to a certain length. And so infrared spectroscopy is not the best technique. You need to find another technique.
Okay, thank you. So the next question we have, could nanotechnologies and nanosensor play a fundamental role in the detection and analysis of surface science phenomena for astrochemistry and astrobiology?
I'm one of the surface scientists who thoroughly believes that nanoscience is basically surface science. Without the technology that we as surface scientists have produced, nanoscience wouldn't exist. But yes, some of the scanning probe techniques, as demonstrated by Professor Honecker in Aarhus, are wonderful in terms of getting microscopic detail of mechanism. It really depends what precise phenomena you want to measure and whether that's feasible. So yes, new technologies will come in, but it's my personal viewpoint is that the suite of technologies that we've got at the moment is not fully utilized.
Mm-hmm. Okay, thank you, Martin. So the next question that we have is the astronomical verification of evidence of polycyclic aromatic hydrocarbons.
If you accept that benzene is a member of that family and being the primary demonstrator of aromaticity, then it's that they're there. However, I will agree with you, there's no single definitive astronomical variation of an identifiable PAH. What we have in what are called the UIRs, the unidentified infrared bands, are basically bands that are consistent with a range of PAH molecules. Typically somewhere between 30 and 50 carbon atoms in size. The only definitive identification of a nanocarbon is, of course, there are identifications of C60 and C70, which are definitive and have been verified. And there are also identifications of C60 plus associated with 1 or 2 diffuse interstellar bands. So no, there is no absolute verification of a single PAH, but there is a consensus that PAHs exist out there because of other things we see.
Okay, thank you. A short still question. What do you think about ion molecular reactions on the surface? So you said that they are probably important on
Yes,
gas.
that's an interesting one. Many years ago, a few years ago, I did some ion molecule chemistry on surfaces. You looked at the interaction of protons with water ice surfaces. And I thought we would get H3O plus, which is what happens if you put an acid into, which is the main ion you get from dropping acids into water. We didn't. We got H2 plus. And myself and the colleague in India who I was working with at the time couldn't explain it. And so we left it as a challenge to the theoretical chemistry community. And I think in passing at an ACS meeting, I mentioned it to David Woon. And David, I think last year or the year before, published a very nice review article suggesting that there is potential for a lot of ion molecule chemistry. The thing is, no one has actually sat down and, apart from Pradeep in India, has got the apparatus to do the experiments. And part of the problem is the ion energies are very, very low. We're talking about millivolt ion energies. And to get energy resolved ions with millivolt energies is tough. So there are experimental difficulties, but it's an interest. There's no theoretical barrier to people looking at this. And I know David Woon has been pushing people to do it. So an interesting question, that one.
Okay, so you think this study could be interesting?
It could be useful, yeah.
Okay, and another question from me. Do you think this experiment with sticking coefficient measurement can be dependent on fluxes of the molecule?
As it's described, the King and Wells experiment, it does not depend on flux. Although, if you increase the flux in the beam, you will compress the time scale of the experiment.
And you can measure it faster.
Yeah. So people tend to do those experiments at relatively, well, typically around 10 to the 12 per square centimeter fluxes. 10 to the 12 per square centimeter per second. So relatively low fluxes, not high fluxes. Otherwise, you just don't see anything.
Okay. Thank you, Martin, again for this very interesting lecture and very informative answers to all questions. I think our time is now coming, but wait, maybe there is some.
No, I think it's just a thank you.
Okay.
Message. Yeah.
Okay. Yeah, I think our time is also over, and I don't see the further questions. So thank you, Martin, once again.
Yeah, no problem at all. Thank you for attending, everyone, and enjoy the rest of the course.
Yeah, have a good day still. Yeah, bye-bye.
Bye-bye.